Thanks, Chairman, for the nice introduction. Indeed, I will talk about post-processing of additive manufactured 3D parts, both on roughness reduction, but also on adding functionality to the layer on the 3D process. And we will do this with ultrasonic spray coating. So I'm a professor in Belgium, in Hasselt University, working in the Institute for Materials Research that you can see here. And in the Institute for Materials Research, we develop innovative and new materials. We, of course, look into how these materials can be used in specific applications. And in my research group, we focus on the printing and the coating of these functional materials on a very broad range of substrates. This can go from glass to textile and paper-based substrates, but also, as I will show in this presentation, on 3D parts, 3D printed parts. If you look at the research group, it's called Functional Materials Engineering. We work on the printing of these inks, also testing systems for these ink systems, also working a lot with commercial partners. And we have a lot of printing installations in the printing group. For flatbed printing, we have screen printing and inkjet printing, of which you can see some examples here. So here you see a device that is screen printed that gives light on a textile substrate. And for example, here you see an organic light emitting device that is developed, as you can see here, with a stack with both inkjet printing and ultrasonic spray coating. So here you see the organic light emitting device lighting up. But today I would like to focus on this ultrasonic spray coating system, because we can use that not only to print on flat substrates, but also on curved and 3D substrates. Okay, so I would like to start with what is exactly the problem, why we will use this ultrasonic spray coating to solve a problem. And then I talk about ink formulation to first reduce the roughness, then also to introduce one functionality, but of course this can be varied. In this case it will be superhydrophobicity. And I talk a bit about adhesion and compare ultrasonic spray coating with standard pressurized spray coating that you all know from industry. And if time is there, I can also talk about some other applications for this ultrasonic spray coating before I conclude my presentation. Okay, so if you look at additive manufacturing, mostly this is performed for low volumes, not really serial production. And one of the biggest issues there is that you, for example, have a lot of manual post-processing. Sometimes you also have automated post-processing, but also there, I think the time to do that, the cost is very high. And to bring additive manufacturing to serial production, to make it, let's say, valuable in industry also for high volumes, I think there are two main problems that should be solved. One is the speed of this 3D printing process, and the second one is the labor-intensive post-processing. And that's, of course, what I would like to focus on. So we work with this selective laser sintered products that we would like to reduce in roughness in the first step. If you look at post-processing, you always have, let's say, a very high surface roughness after your additive manufactured piece, let's say in between 10 to 30 micrometers before you do the post-processing. And then you can do a subtractive post-processing, for example, by sanding or blasting, or you can look at additive. You have lacquering, dipping, but also this spray coating, for example, pneumatic. Today I would like to talk about ultrasonic spray coating. And the reason for that will be coming clear during my presentation. So here you see the working principle of the ultrasonic spray coating system. So you have your ink, which is loaded here in the syringe, and then your ink, this can be, let's say, a solvent in which you have a polymer or nanoparticles sitting. In our case, we use a PMMA as a polymer in an acetone solution, and later we add some nanoparticles. we bring that to our ultrasonic spray coating system, and in here you do an ultrasonic vibration, and that is shown here below in this figure, where you see that the ink flows over our ultrasonic spray head, and by ultrasonic vibration you create standing waves. These standing waves, if you add energy and energy to these standing waves, they become higher in amplitude and also thinner at the top. And due to this thinning effect, you create droplets that spread off. And these droplets, and that's the interesting part of ultrasonic spray coating, because they just pinch off of the generated waveform, they do not have much kinetic energy. So you need a carrier gas. We use nitrogen as a carrier gas to bring these droplets towards the substrate. And if we want to play with ultrasonic spray coating or with the speed of the droplets arriving at the substrate, you can play with the pressure and the power you apply to the carrier gas. So you can choose to have the droplets arriving very slowly to the substrate, and that's exactly what we would like to use here in this story about 3D print. Here you see a quick animation of the system. So here you see the droplets generated, and here you see the deflector with the carrier gas that brings the droplets towards the substrate. And so this is a nice technique that is used in our lab, but you can also use it roll to roll in industrial lab. Okay, let's focus on the substrates. So we use these PA12 substrates using selective laser sintering with, if we measure the roughness just after they are 3D printed, the roughness around, let's say, 20 micrometer. Here you see the profile, and here you see a cross section of the structure, where you see on top, you see this quite porous substrate. And that's why ultrasonic spray coating is this interesting, because what we do now, we take this PVDF as a polymer, and we take acetone as our solvent. And in the second step, we also will use silica nanoparticles to play with the ink formulation. We do that to achieve roughness reduction, plus adding this functionality, the superhydrophobicity, or easy to clean. So the goals of what we would like to reach is a roughness below 2 micrometers. This is set, for example, by Materialize as one of the industrial standards for specific products, 3D printed products in industry. And if you would like to go to superhydrophobicity or easy to clean properties, then you need a contact angle which is bigger than 150 degrees. So that's the focus, or the goals that we would like to achieve. Here you see the parameters of the spray coater. So you have the frequency of the nozzle, which is fixed at 120 kilohertz. Then the power you apply, 2.5 watts, that's the power you apply to generate your droplet. The pressure, that's the pressure we use to focus our droplets towards the substrate, so that the pressure applied to the nitrogen gas. And as you can see, this is very, very small, and that has a specific reason. And then we put 30 layers, and we have a weight percentage of our PVDF in acetone of 4.5%. And then we play with the volume flow, the nozzle speed, the hot plate temperature, and also the height between the nozzle and the substrate. Okay, so if we look at the first results, using 4.5 weight percent of PVDF in acetone, this is still in Dutch. Here you see the roughness, here you see the amount of layers, and you see that if you start with 20 layers, the roughness reduces from 20 to 10 micrometers, and putting more and more layers, you go down to 4.4 microns. We did not reach this 2 microns yet, and if you look at the cross-section SEM images here, this is also 20, 25, and 30 layers, you see that for 20 layers and for 25 layers, your PVDF is a bit penetrated inside the top of your 3D printed part, while with 30 layers you see that you form already a coating on top of your 3D printed part. And I can imagine that if you have very stringent limits, that this is not what you want. So that's why we started playing a bit with adding nanoparticles to our ink. So of course 4.4, if you compare it to 20 microns, is a big reduction, but not the final goal, let's say. So we added nanoparticles. Here you see the amount of nanoparticles into PVDF acetone solution, and you see the roughness. And if we depict it here, then you see, for example, if we put 28 layers having 4.2 weight % of PVDF and 0.8 weight % of silica nanoparticles, that we achieve with 28 layers a roughness around, let's say, 1.8 micrometers, which is lower than this achieved 2.2 micrometer that we would like to achieve. 28 to 30 layers. And doing a cross section, it seems that we have the results that we would like to achieve. So this is the industrial standard that we aim for. But you have another advantage of using nanoparticles. If you look at a surface and you have it very, very smooth, then your wetting is completely different than when you have this structure-like substrate, which has still a bit of roughness. And that's what we try to achieve by using nanoparticles, because if we spray these nanoparticles in this ink, you still have a specific roughness below 2 micrometers, but it's some kind of periodic, and this can help in achieving this easy to clean property. Here you see the contact angle, the water contact angle for the amount of silica nanoparticles you have. And as you can see, we would like to go to this 150, and we have to go to very high amounts of nanoparticles. And here, for example, you see 3.5 weight % of PVDF, 1.5 weight % of silica nanoparticles, and then we show that we go between 20-25 layers, we go above this 150 as contact angle for our water. So is this then super hydrophobic? Well, let's show it in a video. Here you see the contact angle of a droplet, which is sprayed on a normal substrate without these nanoparticles. So you see that the drop, I don't know if it's very clear, but you see that the drop stays on the substrate. While on this one, you see that the drop just rolls off. So this is a clear view that we have increased the contact angle up to 150 degrees and have this easy to clean substrate. So that's, let's say, the biggest difference between both. Here you see it again. So this droplet sticks and this droplets easily flow from the substrate using these nanoparticles. If we do the cross section, then we can see a difference between ultrasonic spray coating and, for example, pneumatic spray coating. And that's the reason why ultrasonic spray coating is so interesting, because of the low speed of these droplets that go to the substrate. These droplets have the time to capillary introduce into the porous surface of your 3D printed part. That means that you fill your pores rather than with pneumatic spray coating, just adding some material on top of your 3D printed part. That is shown here, which means that you have, let's say, better design properties. The thickness does not increase, or the size does not increase, but also adhesion is improved. Here, the adhesion is between the porous surface from the 3D printed part, the PA12, and your added material. Here you really have a good mix of these materials, and the adhesion is improved. So this is, let's say, the reason why ultrasonic spray coating is such an interesting technology to do post-processing of additive manufactured pieces. Of course, this ultrasonic spray coating system can also be used for other applications. We use this impact edge nozzle. But for example, if you go to the vortex, your droplets will not go perpendicular to the substrate, but will be vortexed such that they come in an angle onto the substrate. And that can be used for different applications. For example, here we put a coating specific only on the top on a plunger. I quickly show the results here. So you see this plunger and this plunger. And what we would like to achieve is that the liquid doesn't flow in here, but only stays on top. And that's shown here. So this is the top where you see the coating. Also here, a zoom where you see the coating on this thing. But if you then look in detail and you go lower into these fringes, you don't see the coating anymore. So this shows that you can have selective coating on 3D objects. And also, this is the result where you see some liquid flowing into the pores if you have a coating on top or not. And another option is of course, because of this this vortex that we create, the option to coat selectively only the pillars that you see here. So you don't fill up like we did with the ultrasonic spray coating on 3D printed parts. Here we would like to have a coating only on the pillars without filling it completely. And that's, for example, very interesting for battery research, where you would like to have a very high contact area between two materials with your electrolyte. And here you see the results. So these are the pillars having, for example, a length of, let's say, 20 to 30 micrometers and a width of a few 3 to 5 micrometers. So the aspect ratio is quite high, and you very nicely see the coating only sitting on these pillars. So by showing this, I can say that for not only for 3D printed parts, but also for 3D parts, the options are quite broad. So to conclude, I can say that we used ultrasonic spray coating, which is very interesting because you have a droplet generated, which is very homogeneous and of which you can tune the speed at which it touches substrate. We showed roughness reduction below 2 micrometers for SLS printed parts. We showed that by adding nanoparticles, we could go to a contact angle bigger than 150 degrees, going to superhydrophobicity or easy to clean properties. But we also showed that you can also use it for high aspect ratio coatings, conformal coating, and also for other 3D objects to be coated. So with this, I would like to thank you for your attention, and I would like to thank my group showing here, doing all the research in the research lab in Diepenbeek in Belgium, but also the alumni of my group that were specifically involved in this research, Jeroen Rij Koningen, and then students Sam Slegers, Matthias Linzas, and Dana. So with this, I would like to thank you and open up the possibility to ask questions. Also, can also contact me on this email address if there are more questions after this video. Thanks.
Okay, thank you very much, Wim. Very interesting and let's say very clear how you can do a roughness reduction. Just one question because of the time. How far are you with this project to get this in real production environment, or is it still very much a research environment in itself? Well,
let's say that we have a few companies that have a lot of interest in this ultrasonic spray coating for roughness reduction and adding functionalities to 3D printed parts. But if you look at 3D printed parts that are very difficult, because here I only show, let's say, a flat substrate which is 3D printed. If you start working with curves and holes inside the 3D part and so, then it becomes a bit more tricky. Then you have to play a bit more with ink formulation. And that's why we are heading for a project where we work together with the University in Leuven on, let's say, making an ink formulation and a dimensionless space, so fluid mechanics with dimensionless numbers, to understand how you can tune your ink and tune your ultrasonic spray coat parameters to optimize your layer formation on a specific product. And with this, we have companies like Materialize, De Koning, and other 3D printing companies, ink formulation companies like Agfa and Alnex, that are very interested in developing further together this idea. So I'm open also for other companies that say, okay, we would like to investigate this, because the options are very broad. We had one company that contacted us maybe a few months ago saying, okay, we want antibacterial coatings on there for prosthesis applications. So I think we are not yet there, but there are plenty of options to take steps into the, industrial applications.
Okay. Well, thank you very much. If people want to contact you, the best would be to use your email address, which is below on this slide. So thank you very much, and all the best with your research projects.
Thank you.